Good afternoon, ladies and gentlemen. Thank you very much for attending Sharp Tech Forum today. Today, I'll be serving as the moderator. My name is Hirayama Miyuki. Nice to meet you all. This year, Sharp Corporation marks its 111th anniversary since its foundation. Commemorating this occasion, on Saturday, 11th November, Sharp Tech Day will be held. Currently, Sharp has a slogan, "Be a game changer," and Sharp has been enhancing its development resources, and in cooperation with global businesses as well as startup companies, it is accelerating open innovation, and in the areas of AI, robotics, cross-reality, 6G, food, water, air, green, space, and so on, Sharp is trying to create innovative technology which can transform society. At Sharp Tech Day, it will introduce a future technology strategy and will exhibit innovative products and solutions utilizing Sharp's proprietary technology. Today's forum is taking place just before that event and under the theme of semiconductors, which are drawing great attention from the industry in recent years. We have invited domestic and international experts who are at the front line of industry, academia, as well as government to deliver latest industry trends and future outlook. The first part will be lectures lasting approximately 1 hour and 15 minutes, followed by 10 minutes of break, and we will have a panel discussion and Q&A session in the second part. By the way, we have audience in the venue. There are many online viewers as well. As for the live streaming, it is only available for the first part of the program, which is lectures. By the way, today in this venue, we have the pleasure of having Sharp's CEO and CFO. Let me introduce them at this juncture. CEO, Mr. Robert Wu. CFO, Mr. Brandon Chen. Thank you very much. To start the event, I'd like to invite Mr. Taneya Mototaka, BU President of R&D of Sharp Corporation, to say a few words. Ladies and gentlemen, thank you very much for taking time out of your busy schedule to participate in the Sharp Tech Forum. As was mentioned by the MC, today we have a packed venue and there are many audience watching online. I would like to express my heartfelt gratitude. Thanks to your generous support, Sharp Corporation is celebrating its 111th anniversary this year. To commemorate this year, we are pleased to host today's Sharp Tech Forum event. The theme of this year's forum is semiconductors, which are currently the focus of great attention in the industrial world, which are supporting our lives. I believe that you don't see semiconductors on a daily basis, but AI is creating a major trend, and AI is supported by the semiconductors, and the evolution of semiconductors will be indispensable for our lives, and this is one major technology trend, needless to say, not only limited to AI, but also next generation communications, robotics, and so on. Semiconductors are used as one technology which supports our lives. Against this backdrop, we have invited experts from the government, industry, as well as academia, and we will discuss trends of semiconductors and what sort of world we will have in the near future. We will receive such lectures, and at the very end, we will have a panel discussion including sharp engineers. First and foremost, the first speaker is from Foxconn Group, Chief Semiconductor Strategy Officer, Dr. Shang-Yi Chiang, has kindly agreed to give a keynote speech under the theme of From Integrated Circuits to Integrated Chiplets, how new LSI world is being carved out, and the world towards that he will be talking to this theme. Next, we have also invited a Professor Katsuaki Suganuma, Professor Emeritus of Osaka University and Director of the Flexible 3D Packaging Collaborative Laboratory, Institute of Scientific and Industrial Research of Osaka University, will give a presentation titled Next Generation Semiconductor Packaging Technology Pioneered by Collaboration on the Evolution of Industrial Technologies and a new future vision of next-generation semiconductor packaging technology through collaboration, and discuss what sort of world will be arriving shortly. And then the third and last presentation will be Mr. Hisashi Kanazashi, Director of Information Industry Division, Commerce and Information Policy Bureau of Ministry of Economy, Trade and Industry. Will introduce the theme of prospects of semiconductor industry strategy to win in the global era, and in the near future, how will Japan's semiconductor industry evolve, and what sort of direction does METI aim for? He will be discussing these themes with us. Of course, amongst amid a major global trends, semiconductor competition is very fierce, and Japan, as a country, enjoys what kind of strengths? That is an important question, and he will be talking to this theme. In the panel discussion, we have invited our engineers from AI, communications, as well as implementation technology areas. Our speakers are well versed in these areas, so with a total of 6 panelists, we will be talking about the direction of semiconductors as well as LSI technologies and expected applications. And finally, we will have a Q&A session with all of you in this venue, and I'm looking forward to such discussions. In today's event, we will be discussing the semiconductor trends as I just laid out, and near future outlook, and so on. And I hope that this forum will be useful for you in terms of inspirations and future directions and so on. This is a 2-hour program, and I hope that you will enjoy this forum. Thank you very much. Thank you very much. Now let's proceed with the program. The first part of the program is a keynote lecture by Dr. Shang-Yi Chiang, Foxconn Semiconductor Strategy Officer. Dr. Chiang completed his PhD in electrical engineering at Stanford University in the US. He was engaged in semiconductor business at American Texas Instruments as well as US Hewlett-Packard. Then he returned to Taiwan in 1997, and Dr. Chiang served in positions such as Senior Vice President of Research and Development, as well as Co-Chief Operating Officer at TSMC. From November 2022, he has served as the Chief Semiconductor Strategy Officer of the Foxconn Group. Today, he will be speaking on the theme of From Integrated Circuits to Integrated Chiplets. Now, Dr. Chiang, please come up to the stage.
Doctor, the stage is yours. どうぞ皆さん、大きな拍手で。
Please welcome Dr. Chiang with a round of applause.
Good afternoon, ladies and gentlemen. Welcome to Sharp Technology Forum. My name is Shang-Yi Chiang. It's my great honor to be here to share with you some thoughts I learned 50 years in semiconductor industry. I'm a very old person. I think we face the biggest change in semiconductor industry in the past 50 years since I have worked in the industry. And I'd like to share with you what I saw. And maybe that means a challenge, and it's also opportunities. The next, first is the semiconductor IC environment is changing. Then I will introduce a concept of integrated chiplets. It needs to build an entire ecosystem to win, and I will share what. The biggest change right now is we all heard about the IC, silicon IC scaling. It's better known as Moore's Law. And Moore's Law is getting close to its physical limit. As Dr. Moore just passed away a couple months ago, unfortunately. Well, it's nothing to do with his passing away. It's because in the last few decades, in the last 40, 50 years, the entire electronics industry was doing very well. It's mainly because of Moore's Law. We have this silicon IC technology, be able to, every 2 years, go to the new generation. And the circuit will be faster, consume lower power, but most importantly, it becomes cheaper. Almost anything else you buy, you don't find anything else get cheaper every year. It's always inflation. But this is a very few exceptions, it gets cheaper. And for example, this generation of the semiconductor chip, the next generation, it can shrink to half of the size. That's why it gets cheaper. But usually the company, they do not just simply shrink to 1/2, make it cheaper. Because if you have a cell phone, you make it a little bit cheaper, people are not going to buy it. Instead of make the die smaller, they make it, after they shrink it, they make it a bit bigger, so they add more functionality. That's why I encourage everybody to buy a new phone. Also, because the performance got faster and consume lower power, you develop more and more applications. That's why it fueled the very booming of the electronics product, all because of Moore's Law. Now the Moore's Law is getting close to its end. Why is it getting close to its end? It's a very simple way to explain that is we all heard about right now, Japan started this 2-nanometer technology initiative. And what 2-nanometer mean? Well, supposedly 2-nanometer means it's a minimum dimension is 2 nanometer. That means 4 atomic layers. 4 atomic layers just used to be that way, but right now people call it 2 nanometer, 4 nanometer, 5 nanometer. It's just a marketing purpose. They don't really go by the minimum dimension. But if 2 nanometer means 4 atomic layers, usually if you try to make it work, there's a very tight spec. And roughly speaking, the spec is plus minus 10%. If you make 2 nanometer, you can have plus minus 0.2 nanometer. And that's less than 1 atomic layer. So when you go to 2 nanometer, really you cannot go any further. That's why I approach the physical limit, because every atom occupy 5 angstrom, means half nanometer. So that if the Moore's Law is getting its close to its physical limit, then impact this industry. We cannot enjoy every 2 years, the performance got improved a lot, and power got dropped, and cost become 1/2. All this will go away. So we need to figure out how to react that. And this is really the biggest thing I ever seen in semiconductor industry, 50 years I've been involved. Besides that, we can see like now, if we see from the leading edge technology, they're working on 4 nanometer technology. What do you mean? If you design a circuit using 4 nanometer technology, very, very expensive, because you have the tens of billions of transistors. You need to invest a lot in design tools. You need to hire a lot of people. A typical 4 nanometer development cost is about $2 billion. And a typical, the R&D expense for the design company is about 20 to 25%. So that means if you design a 4 nanometer circuit, you have to sell for $10 billion to be able to recover your development investment. And so that means a very large volume product. Only large volume product can enjoy using 4 nanometer. When you tape out a 4 nanometer technology, the photo mask costs you like $15 to $20 million just by the photo mask. So the designer usually very, very nervous. I was told by my older customer, after he taped out, he couldn't sleep for 3 months before he got a wafer back and test, make sure it works. Because if he makes a mistake in the design, his company has to pay another $15 to $20 million for another set of masks. So he can only pray, hope it works. It's a pretty high pressure. So again, for how many products you can sell $10 billion? $10 billion means probably you have to sell more than 500 million parts. Only like cell phone, you can sell that much volume because all the different brand cell phone, they use pretty much the same chips. So going forward, there are not many products can enjoy the 4 nanometer, 3 nanometer, 2 nanometer technology. Meanwhile, because every electronic product, they very much depend on, for the next generation, very much depend on the advance in the IC technology. So they wouldn't take risk to change everything else. So now we look back, the system design, architect has not changed too much. It's still basically, for example, use the logic-centric, CPU-centric system design. Today, there are many applications will be much better off use memory-centric system design, but it's not available. Because during this development, every product design, they just use the next generation IC. They don't have time, and they wouldn't take the risk to change anything else. Because they do that, if they run into trouble, their competitor will win. So the system design and the package didn't change too much. The package industry, usually they work very hard to reduce the cost, but they do not advance the technology too much. So after 20, 30, 40 years, if you look back, the package is a bottleneck in some applications. When I worked at TSMC in 2009, this is 14 years ago, we began to realize that at that time, this graphic chip is one of our biggest customers, and they are the technology driver for TSMC. And I noticed that for the graphic module, at that time used 45 nanometer technology, and it's one GPU drive 8 DRAM. If we're trying to do some simulation, for GPU is one of a particular case. you need to pass the data very frequently between GPU and memory. You pass the data to DRAM and get the data back. So we did a simulation. We find out that just pass the data, GPU run very fast, and memory react relatively fast. But you send a signal between GPU and the memory and back and forth. It's all 40% of your speed, 60% of your power. And that's about equivalent to if you 2 generations IC technology. So we began to realize that's a big, big bottleneck. And we're trying to look at why, because we see the reason is the package on PC board or substrate. That's how you connect between GPU and DRAM. The metal pitch is about 110 micron. And because such a wide metal pitch, you need to fan out a couple thousand metal lines from GPU to DRAM. And if your metal pitch is 110 micron, you have to put the DRAM very far away. So you also, the 110 micron metal pitch means the metal width is 50 micron, half of that. So that began to have a very high capacitance. And so it consumes a lot of power. That's why it becomes such a bottleneck. Then we think I can do that on silicon wafer. The metal pitch on PC board and the substrate is about 110 micron. The technology on silicon wafer, we can easily do 110 nanometer, which is 1,000 times better. And the metal density is a 2-dimensional. So that means the metal density on silicon technology is 1 million times better than the package technology. So we realized there was a gap because the package technology, they spend so much time in improving the cost. They don't shrink too much. So at TSMC, we established a program to do the advanced package. What it means, we say, well, I use a silicon substrate to replace the PC board and the organic substrate. Then I can put the DRAM and GPU very close to each other. And that works. So TSMC rolled out a technology, the code name is CoWoS. I'll show it a bit later. So this is just one example. We found actually the package become a bottleneck. So we developed something we call advanced package to open up this bottleneck. Okay, this is a technology change. But at the same time, we found that the market has changed. Used to be from mainframe computer to desktop to PC to smartphone, it's the same product. But right now, it seems like the biggest market is IoT or AIoT. They are very, very diversified. So we cannot find a single product you can sell for $10 billion because they're so scattered. So that's become a challenge from application side. So from the technology side and from the application side, then we began to figure out these 2 major changes, Moore's law getting close to its limit, physical limit, and also the application becomes so diversified. From these two changes, we found the current, this ecosystem cannot support the new product going forward. So we need some changes. Okay, this, I spent much time on the last view graph that this one will be easier because I already said in 1980s that there's always a technology driver for the IC technology. And in the 1980s, and before, it usually was a mainframe computer, then became a desktop, became a PC, feature phone, smartphone. In all these cases, they are kind of single product, single type product. Maybe there are many different companies working on that, but it's single product. And they are very similar. They can use the same chip, they can share the same chips. And usually in this case, the market is dominated by a few large companies. I used to be dominated by IBM, by Apple, HP, Dell, from time to time. Now when it comes in AIoT and IoT, they will be very diversified. You will have you will have different like the IoT, personal product, smart home, smart city, smart car, or industry application. And in each category, there are hundreds of different products. So these are very diversified needs. It's harder for us to find a single product you can sell for a few 100 million parts. So this is a big change. I just what I mentioned in the previous view graph. Next, again, I already said that we found this is a GPU on the upper left corner. One GPU drives 8 DRAMs. You can see how far away they are. The reason I say far away, if you look at the view graph, they're a couple of centimeters away. But if you compare to, they're on the same chip. They are far, far away. If we use that on the right-hand side, I replace a PC board by a silicon substrate. So we call it silicon interposer. Then they can be put almost right next to each other. Then your speed is improved when you pass the signal back and forth, or your power consumption is significantly reduced. The performance becomes very close to they are on the same chip. And that's a very significant. Actually, at TSMC, when we first developed the advanced package technology, we only had one thing in mind, to improve GPU module. We didn't realize today the AI benefit more than graphic chips. But AI basically use graphic kind of architect, pretty much similar. Also, until we did that, we began to realize in the past, there's a golden rule for IC players. If you can integrate 2 chips into one, it's always better. If you can integrate 3 chips into one, it's even better. But with advanced package technology, after we did that, we began to realize today's product, in many cases, if I divided one chip into 2, I'm much better off. And this, again, we didn't realize when we developed advanced technology. This is just by pure luck. Sometimes you win by have a good luck. Sometimes you lose with a bad luck. I give you one example, like for smartphone, there's a main chip. One is AP, one is it's modem. And the modem chip, you have about 1/2 is a digital, 1/2 is analog. For the analog part, you go to the next generation. Analog, you cannot shrink, because if you shrink, you lose the resolution. And also analog, you need a large delta V. Every time when we shrink, we lower the VCC, the driving voltage. So when our major customer developed the modem for smartphone, when you go to the next generation, the digital people are very happy, and analog people are very painful. For analog, they go to that, they don't benefit very much. But because of the lower VCC makes the design very difficult. So in the entire development cycle, the analog design consumes more time and effort than the digital part. So with this advanced package technology, people just realize for the modem, what if I divided this chip into two? And the analog part, you stay, do not migrate to the new node. And you only migrate the digital part. You are much better off. You save one half of your design cycle. Also, your analog part, you stay in the older generation, the cost is lower. Also, in the beginning, when you migrate to the new node, the defect density is bad. So your yield is low. By shrinking the chip into half, your yield is more than doubled. So I'm sorry, I shouldn't say doubled. It's a square root. For example, if before you split these two, your yield is 64%. After you divided the analog and digital, your yield, digital part of your yield will be 80%. 0.8 by 0.8 is 0.64. That's a relationship. So that we began to have the concept of chiplet. That means if we divided one chip into two, divide into three, divide into four, you are much better off. So this is the chiplet concept is really come out. It's a pure luck. It wasn't really the beginning. We had that in mind to develop the advanced package technology. So I give another example. What is how we can use a chiplet? For the IoT system, they have I say we have thousands of different products, but they also have something in common. IoT means you always take you have a device, it's a periphery, then you collect some signal with different sensors, and you send it to the cloud, the data center, do some operation, then send it back. So they have something, even though you have 1,000 different products, you have a lot in common. Most importantly, you all need a controller, or you can call it MCU, you can call it AP, whatever. And then you have the A to D, D to A, a lot of sensors. You have the power management chips, your memory, and you have the Wi-Fi communication part, or Bluetooth, all these things. But the difference is, in each category, the requirements are different. For example, it's, when you talk about the automotive, the self-driving engine, you need a very high speed. So you need a very, very high performance AP to drive that. And for a simple device, for the one like you do the exercise, you monitor your heartbeat, you monitor then your speed, is how many steps you worked. And you only need a very simple controller. So then for the A to D, D to A, sometimes you need maybe you need a 16-bit A to D, 32-bit A to D to A. Sometimes you only need 4-bit. If I take this entire SoC into these major categories, maybe 8 to 10 of them, then I make the, for each category, I make the, for the controller, I make 6 different versions. For A to D, D to A, I make 8 different versions. I put them together like a Lego using the advanced package technology. Then it will allow me to, we can put together this entire system by this kind of Lego approach. For example, if this customer come over with a special application, if I do the business for the foundry to system foundry business, if we do that. If Sharp become a system foundry player, Then there's a customer come over. I build this as a chiplet die bank. I have them available. I already buy these chips. Well, it's not a whole lot, maybe 30 of them. I build up this bank. I don't really need a big volume because in the early stage, if the customer come over, he only need about 1,000 parts as a sample. Give to his customer or to develop the application software. He doesn't need a lot. So if the customer come over, I'll say, oh, because from your need, I know the controller unit number 2, memory unit number 1. Then I put them together use advanced package technology. What it helps is if you tape out, if the customer do the SoC, this tape out, it design, you need to hire maybe 40, 50 designers to design. And take him 1 year or more than 1 year to design. And then when you tape out to TSMC, to Samsung, it takes him 3-4 months to get the wafer back. Then take him 1 or 2 months to debug. That's 1.5 years already. And he has another 6 months to develop the application software or these things. So we come to shop, I do the system foundry business. I can just pick up from my original die bank. The advanced package process only take 1 month. You can get your system back. All these dies are available. So to my customer, he doesn't need to hire 50 engineers, save him a lot of money. He doesn't need to spend $15 million only on the mask to tape out the TSMC. And he doesn't need to spend 1 year to design and 6 months to get a wafer back from TSMC. So in 6 months, he can have the prototype product in his hand already. As you know, most of the product, the time to market is most critical. So in this way, your customer will be able to hire less people, spend less money, and get their prototype in much, much faster by taking advantage of the integrated chiplet technology. So this is just give one example. Okay, this is why IC is for integrated circuit. You put a different circuit, transistors, resistors, capacitors on one piece of silicon called integrated circuits. And we had an advanced package platform. So by integrate chiplets together, so we call it integrate chiplets. And this entire integration is a system level integration based on advanced package platform. So this is a concept of the integrated chiplets. Again, so repeat what I just said is looking for the overall system design hardware. It can be partitioned into different units, like I just used the example of the IoT device or AIoT device example. We participate into about 10 pieces. And each piece, we develop a die bank for a couple of choices. Then we use the advanced package platform to put them together with a performance very close to they are on the same chip. But I do not need to design this entire chip. In some way, it's a concept a little bit like you put the IP into a hardware called chiplets. In this case, you really can connect all these chiplets, and you can try to achieve the optimum overall performance. We think this integrated chiplet approach will become will be a trend I'm not trying to say this will replace everything. It will not, because we have all the product so complicated. This may help some special product, but will not replace everything. Again, okay. Let me say what are the advantages. We can use the advanced. Number one is there are two concepts I'm trying to say. One is use a GPU or AI example. The advanced package technology help to enhance the system performance. As I just said, like a GPU, because we can put the GPU and the DRAM close to each other, you can save 40% of the delay, you can save 60% of the power consumption, and that is improve the performance. But this is only for a few cases, like the GPU, CPU, and AI engine. For many others, it didn't really make too much difference. This is one. So one is to enhance the performance. And number two is it's a module approach. Give you a very good flexibility and allow you to put together you can use kind of like a Lego approach. And we realize it able to, like if I break, like the example I showed earlier, if I break the IoT into into 10 parts, I can use the CPU, I can use 5 nanometer technology. For the power management, I can use 0.18 micron technology. For each different parts, I can pick whatever the best technology node, optimum for performance and cost, very important. And I can even use 3-5 compound. I can use gallium nitride, gallium arsenide for optical application, and I can use silicon carbide for power management. I can integrate all this together for the best performance and optimum cost. So this is called heterogeneous integration. So these are the couple advantages we try to emphasize. What it takes to make it happen? First, we need to build up the entire ecosystem. Why silicon IC technology is so useful today? Because it has a very complete ecosystem. It's built in last 40, 50 years. You have the material, you have the process equipment, and you have the CAD tool, computer design aids, and you have the silicon wafer package design with testing with all this. This is the entire platform. And we try to promote the chiplet technology. You need to build up this ecosystem, this platform. Because, for example, like how do we interface between these chiplets? You need some standard, and you need TCAD tools to do your design optimization, these things. So everybody really to work together. It's more than one company can do that. Everybody had to partner together to make it happen. So whoever can put together this ecosystem will be the final winner. Again, what I'm trying to say is the silicon IC technology scaling is really has been the main engine to drive the electronics product to have such booming the last 40, 50 years. Now it's getting close to its end. I'm not trying to say chiplet will replace that. No, it's not the case. I think we are waiting for the younger generation, most of you in the audience, to have innovation to replace the silicon technology. we hope. Before that happened, we find this more like an incremental progress. You're trying to optimize, or we found that the bottleneck is package, and we think the system design has some room to improve. So when we are waiting for the big innovation, we can try to improve this little by little, and from package side, from system design side, to improve the entire system performance. And we're waiting for the big innovation. So that is my point. Well, thank you very much.
ジャン博士、ありがとうございました。We thank you very much for your inspiring presentation, Dr. Zhang. You may now
Do
leave
I
the
wait
stage.
for a question or I don't?
Not later?
I just go.
Yes. Thank you so much. どうぞ皆さん大きな拍手で。
Please give him a big round of applause once again. Next, we will have a lecture by Professor Emeritus Suganuma Katsuaki of Osaka University. Professor Suganuma completed his doctorate in nuclear engineering at Tohoku University in 1982. After working as an assistant at the Institute of Scientific and Industrial Research of Osaka University, he became an associate professor at the National Defense Academy of Japan and a professor at the Institute of Scientific and Industrial Research of Osaka University before assuming the position of director in 2018. He has led numerous national projects in areas ranging from materials processing to applications and has also held key positions in ISO and IEC activities. He has served as the director of the Flexible 3D Packaging Collaborative Research Institute at the Institute of Scientific and Industrial Research of Osaka University since 2020 and as the director of the 3D Packaging Technology Division at LSTC since 2022. Today, he will be speaking on the theme of collaboration to open up the next generation semiconductor packing technology. Now, Professor Suganuma, the floor is yours.
Thank you for that kind introduction. My name is Suganuma from Osaka University, and this is also Institute of Scientific and Industrial Research that I have been working for. I am a part of the management of the institute. First of all, I'd like to congratulate on the 111th anniversary of SHART Corporation. You have a wonderful technology. Our institute have 80 years of history. Your history is much, much longer than ours. As you know, in Kansai area, the west part of Japan, electronics industry is very, and has been very active. We can work thanks to electronics companies, parts manufacturers, equipment manufacturers. All of these companies have worked together in the past, especially Osaka University focused on packaging technology. And that is really the basis we have been working together to lay down the foundation. Today, I want to talk about the next generation semiconductors. There was in detail keynote presentation. So today I would like to only focus on these two topics. And later I'm looking forward to have exchanges of views later on during the panel discussion. So packaging technology is part of implementation, which is very important for semiconductors, especially for power semiconductors and advanced semiconductors, which are really the strengths of Japan. So materials, processes, know-hows for packaging technology, and furthermore, reliability of the product that are produced. All of these need to be maintained and enhanced into the future. That is what I hope for. So that's what I want to discuss in my presentation. Every day in various media and newspapers, we received newspaper. This is an example of news in May, when G7 summit was held. Prime Minister welcomed major enterprises from the rest of the world for discussion. Many companies indicated their intention to invest in Japan. And what you see here on the left-hand side, the CEO of Intel said that they are going to set up an office or post-process or back-end process factory in Japan. So that is packaging line. The packaging has been built with an ecosystem of companies, and we have built that packaging technology in Japan. That is why global companies are willing to invest. It's not just we universities. We have been working with industry partners, and our wish is to create the new world. We want to be part of this new world. So that is what is happening today. And another thing about packaging, there is a clear example in the United States. NSTC last year, a little over a year ago, was established. There has been substantial investment made. The organization has not been completed yet, but this is a publicized document. NSTC, National Semiconductor Technology Center. NSTC, including next generation technologies, is going to support whatever needed in the semiconductor industry. And the investment size for NSTC is $2 billion, pretty substantial. There are other organizations as well. On the right-hand side, NAPMP, National Advanced Packaging Manufacturing Program. This was also an organization established for advanced packaging technology. They actually have larger budget than NSTC. Their budget size is 2.5 billion yen. So United States understand there has been a gap of packaging technology and its process. So to build an ecosystem, they need to focus on packaging sector. There are other examples. 19 billion is the total size for this semiconductor industry. So that's the case from the United States. Now, within Japan, it's not just LSTC. Osaka University is working with various companies, trying to understand where we need to strengthen, where we should explore the possibility. There has been the keyword mentioned, Chiplets. TSMC created this major breakthrough in semiconductor industry. Originally, though, semiconductor manufacturers were quite successful in Japan. They had built many elemental technologies for semiconductors. So the question is how we can utilize Japan's strengths so that we can go global and compete with global companies. So within LSTC, what we should do, we are actually discussing over this question. If you have any specific suggestions, if your company have specific technologies, please do contact us. If you look at this diagram, illustration, there is need to explain. It's obvious. We have multiple technologies where we need your support, especially reliability, which is indicated by red color, is important. For advanced semiconductors, AI is going to help develop our industry and autonomous driving as well, especially when it comes to automotives. It is also a life and death technology. When a semiconductor makes a judgment, the judgment must always be a right decision making. So high quality semiconductor making is indispensable and essential, and that's where we have the strength. So again, our wish is to have exchanges with you so that we can collaborate to develop this technology. This is an excerpt from last month Nikkei Crosstech article, utilizing Japanese technology, how we can develop next generation technologies. The article itself, I just copied and pasted that article. But on the right-hand side, I have listed some discussion points based on this article. With regard to the replacement of interposers, how can that replacement create the bridge structure? Advanced semiconductor companies do have their own ideas for bridges. They have been able to commercialize some of those technologies. And they have proven already that results in much faster speed and performance. So bridge is something that comes out of Japan. We need to appeal to the world that this is the Japanese technology. And also RDL as well, redistribution layer. Each company has its own stacking, its own structure, and that's where we might always find new materials and interfaces. So when it comes to hybrid bonding as well as substrate, RDL as well, all of these used to be the area where Japan was quite strong. We were always the number one to propose new technologies in those areas. So let's utilize our strength. This is another example from Apple M1, which was the CPU launched last year, which actually connects two silicons. You can't see the bridge structure, but CPU performance and GPU performance, as you can see in these data or graphs. This is a simple example. Power consumption is much smaller, and performance is much better as a result. So that's a new packaging structure and materials, what they can do to achieve. We want to go ahead and generate a new world. So chiplets, how can we create chiplet structure cheaply and with high reliability? US is leading this effort. As you can see, there is a standard making organization, UCLE. The already first version is just about to be publicized. So standardization is progressing. Again, we want to be part of that effort that is making progress. This is my last slide. I talked about reliability early on. What is important about this is when you think of logic, making logic in 3D is extremely difficult. So it's not just wiring, it is more about fighting against heat, unless not like memory. So how can we overcome the heat problem in terms of logic 3D? I think it's more about materials and structure. On the upper left-hand side, you see IRDS forecast some time ago. It shows CPU computing power and performance with one CPU, 1 teraflops. This is the level achieved only by old supercomputer in the past. But if we are not able to overcome heat, we will not be able to elevate that computing power further. In other words, the line stays in there, in red line. Heat affects CPU power as well as reliability. So think of autonomous driving and other applications where a social infrastructure should not be broken. That AI or CPU or GPU, we should be able to propose unbreakable CPUs for these applications to the world. And that can be supported by human resources. You see a map of Taiwan. There are 4 top universities in Taiwan. Last fall, I spent about 4 weeks in Taiwan. I was invited there and stayed there some time. In south and middle part of Taiwan, close to major universities, there are major enterprises sitting next to them, growing together. In the south, there is Cheng University. Cheng University. The students are very active. I really envied them. For a whole nation, they are dedicated to semiconductor development. And this is something that we should learn from Taiwan. We would like to establish a center like that. And at the bottom of the slide, you see IMEC example. You see the IMEC is actually almost co-located with top university, Leuven University. Distance is very important, physical distance. When people grow, wonderful technologies will also grow. So that's something that I'd like to see in Japan. I think I'm running short of my time. So LSTC, basically this is an open organization. Rapidus is a new semiconductor company to be established in Hokkaido Island. And to support their production, LSTC is going to play an important role. This is an open organization, so it can provide services to material, process, user companies. So again, we would like to establish company-to-company collaboration. And also, we would like to promote the packaging technology that world expect of us. Thank you very much.
Thank
you very much, Professor. And please give him once again a big round of applause. Next, Mr. Kanazashi Hisashi, Director of Information Industry Division of Commerce and Information Policy Bureau of Ministry of Economy, Trade and Industry, will give a presentation. Mr. Kanazashi joined the Ministry of International Trade and Industry in 1998, after which he worked as a visiting researcher at Stanford University. He also received his MBA from EDIC Business School in France. Since 2009, he has served as a member of the Industrial Revitalization Division of Economic Industrial Policy Bureau and as a member of the Policy Planning Committee of General Affairs Division, Minister Secretariat since 2014. He has served as a planning officer at the Japan Economic Revitalization Secretariat, Cabinet Secretariat, Deputy Director of JETRO Los Angeles Office, Director of Industrial Creation Division, Economic and Industrial Policy Bureau, and Counselor in charge of Information, Industry and Digital Economy and Security, Minister Secretariat, before assuming his current position in July 2022. Today, he will be speaking on the theme of prospects for semiconductor industry strategies to win in the global era. Mr. Kanazashi, the floor is yours, please. Well, thank you very much for your kind introduction. I am Kanazashi of METI. Well, thank you very much for your cooperation always. So today, I believe that all of you are engaged in semiconductor work. I believe many of you are like that, and also there are many of you who are knowledgeable about semiconductors. And Japan and for the rest of the world, what sort of cooperation has been taking place and what sort of promotion has been taking place. I believe many of you are abreast of such topics, but for refreshing your knowledge and so on, I would like to introduce some of the initiatives that we are promoting. So, semiconductors. There are two keywords that we recognize to do policy making, to conduct our policies. That is speed as well as continuity. These are two keywords. I will talk about them later on, but at the Kumamoto University, Kumamoto TSMC plant building is taking place smoothly, and last June we decided to support TSMC factory building. Semiconductor situation has started changing rapidly about 2 years ago, and over the past 2 years, last year TSMC support was decided, and as was mentioned by Professor Suganuma, in his lecture in May, there was a Prime Minister's office meeting, and while considering international cooperation, initiatives are underway. So we need to be speedy and also have to think about continuity. And currently there are 3 steps, step 1, 2, and 3, to conduct our policies. Step 1 is, it says IoT, and Japan's industry, including the future, has to think about what sort of semiconductors will be needed. So we should secure enough supply capacity. So that is about strengthening production foundations for the time being. That is step 1. And step 2 is Rapidus. Rapidus is the company, a new company, and you may recognize the name Rapidus. But Japan-US cooperation, and not just Japan-US, but also including Europe, on a global basis, globally top-level cooperation has to be pursued so that leading-edge semiconductor can be implemented. That is what step 2 is all about. And then step 3 is more of a midterm effort. So post-processing, packaging, and supporting materials and devices and equipment, we have to think of all these, and we should leverage Japan's current strengths based upon which, going forward in the future in the domains related to semiconductors, technology innovation has to be brought about based upon Japan's technology. That is our aim. So this is more of a midterm development efforts, and this is positioned as step 3. So step 1, as I said earlier, as you can see on the left-hand side, this is a TSMC Kumamoto project. That is a flagship project for step 1. Sony and Denso are working with them by setting up a joint venture, and then the company name is a JASM. Joint venture name is a JASM. And as you know, Sony does smartphone camera sensors. They produce such sensors, and assembly is made to logic semiconductors, and with that in mind, they are pushing for cooperation with TSMC. And then so, little by little, is seeing the evolution of logic use in automotives in the area of a micron 28 nano is becoming more of a reality. So eyeing that they are making efforts with Sony and Denso. Overall, the budget size is 476 billion yen, and this decision was made earlier, and this decision was made in June last year. And the plant itself will be operational at the end of next year, 2024. And construction site and people at the front line are supporting this endeavor to a great deal, and construction is making a steady progress. And apart from that, memory bases exist in Japan, so major support is being provided one after another. That is the current situation we are in. On top of that, chip manufacturers are also supported, but on top of that, for the time being, production equipment and the materials and the parts are also an area where we believe that the demand is expected to grow. So with like-minded countries and like-minded regions, for their supply chains, Japan has responsibility to supply products, and we need to fulfill such responsibility, and the central government wants to support that. So regarding equipment and parts and components, we are also rolling out support one after another. So that is what step 1 is all about. On top of that, talking about step 2, Rapidus is one example. So far, last year, already 70 billion yen budget was secured, and from this year onwards, 260 billion yen of a budget was newly added for Rapidus. So little by little, project is making a progress, and we are encouraging and promoting the progress of the project. And for the time being, on the left-hand side in the column, that is Hokkaido Chitose city where building is taking place, because we've selected this location, and with the US IBM, and also as was mentioned by Professor Suganuma, IMEC is another partner, which is energy advanced semiconductor development, global top-notch research and development base. And we are working with IMEC and also from FOFA and France RESI. We are working with Western research institutes and labs, and in collaboration with them to nano, logic and semiconductors related efforts are being made to realize such a technology. And this year, which is a middle box in New York, there is an IBM Albany Research Institute, and Rapidus has already dispatched dozens of researchers or engineers. And also from IBM, more than double of such researchers are visiting our site, and in cooperation with IMEC, the market sought by Rapidus is considered when designing production processes. Such specific efforts are underway. So up to this point, the project has been making great progress. On top of all these, as was mentioned by Professor Suganuma in his presentation, the front page of Nikkei Shimbun newspaper was featured, but on the 18th of May, this year, immediately before the G7 meeting at Prime Minister's office, semiconductor-related meeting took place. Against this, in this meeting, TSMC talked about the customer needs and government support, and he said that he wanted to expand investment in Japan. As was mentioned by Professor Suganuma, Intel and Samsung are considering post-processes, and they want to expand their efforts in Japan. Such intentions were expressed, and 500 billion yen investment will be made by Micron in Hiroshima. They made this announcement back then. So on our part, now global top manufacturers are engaged in Japan to make efforts in cooperation with overseas organizations. We are thinking of a next step, trying to substantiate such a step. And then on the right-hand side, IMEC and IBM, they are Rapidus supporters now. And as I mentioned earlier, regarding Rapidus efforts, they are making steady progress. So on the day, Prime Minister said that the government as a whole will try to support semiconductors on a continuous basis. So going forward, after the summer, there will be a budget-making season, and what's needed for next year or budget amount should be secured. And against this backdrop, what is the global situation? There are several points that I want to talk about at the G7 this year. For the first time in the history of G7, talked about economic security for the first time ever. So in that sense, this G7 was a very historic one. Against this backdrop in the world, partnership has to be sought to build resilient supply chains. Supply chains have to be strengthened, so without becoming inward-looking with relevant countries, especially countries with which Japan shares fundamental thinking, we would like to expand a partnership with them. Also, various countries, as was mentioned by Professor Suganuma, NSTC was explained, and finally, across the regions and countries, budget has been secured, and they will become more substantial and specific. On our part as well, we would like to expand mutual efforts and initiatives. So Japanese businesses outside of the country conducting activities should be supported by the budgets prepared by foreign governments. I believe that this is very important, and we have steps 1, 2, and 3. And in implementing them, we would like to cooperate with overseas organizations and governments, utilizing our own budget as well. So, with economic security in mind, we would like to strengthen our mutual efforts. And up to this point, with these themes in mind, on top of the G7, including the US, with various countries, Japan has been expanding partnerships. In principle, with the US, as you can see at the very bottom, the third bullet point, we should respect each other's recognition and efforts should be complementary. This is extremely important. So based upon this thinking, starting with the US, Japan has started cooperating with other parts of the world and countries. Of course, even with countries without MOCs, for example, Taiwan or the ROK, mutual and interactive discussions have started taking place. So we would like to appreciate these partners and their efforts. And recently, there have been a lot of developments with India. So I myself last month visited India. So newly, India is another partner which we are acutely aware of so that we can expand our cooperation with foreign countries. Finally, I have been explaining semiconductor topics all along, but the most important point is the industry which actually uses semiconductors and their green and digital transformation. How to promote their transformations is very important. So in that sense, the second bullet point on this slide says that AI and edge technology are making a progress and evolution. So customer chip demand will expand depending on applications and digitalization and green transformation in mind. How to leverage state-of-art and leading-edge semiconductors has to be considered by users themselves. We live in such an era, so not just pre-processing but also packaging included. We live in such times. So when implementing our policies for semiconductors, the applications of semiconductors has to be expanded. This is something we keep in mind, and in the end, overall, the industry should go through digital and green transformations. Also, later on during the panel discussion, I will be participating. So when we have the discussion, I'd like to introduce Meti's thinking and all of that. Thank you very much. Thank you very much, Mr. Kanazashi. Please come off the stage. Please give him a big round of applause once again. That is all for the first part of the program. I have an announcement for online viewers. Sharp Tech Forum live streaming is now coming to an end. By the way, regarding today's forum, there is an online survey. So there is a QR code or 2D barcode, and you can access the survey through this QR code. Well, thank you very much for taking time watching our program today.